Hello, hopefully I'm audible. So let's get started. So today, before starting, let me introduce myself. Hello everyone, myself Supratim Roy. I'm a third year mechanical engineering student in Tejpur University. So today I'll be showing everyone that how to make this structure in ANSYS and apply forces and show a simulation of it. So let's get started. So as it's a static structure, we'll be working on static structure. Let's check if there's any engineering data provided. As you can see, it's Young modulus and Poisson's ratio has been given 20 to 10 to the power 5 Newton millimeter square and 0.3. So let's make it as sign material, and that sign material this is the Young's modulus. So as Newton millimeter square is not available, we'll do it in megapascal. So it's the same as Newton millimeter square. That will be 20 to 10 to the power 5 2 3 4 5, and Poisson's ratio is 0.3. Okay, so assign our engineering data. Now let's start the geometry. Okay, so this is the XY plane. So let's check. Okay, so as we need to make two beams of diameter 15 and 10 millimeters. So as it's given in millimeter, we need to convert the unit into millimeter. Now let's start sketching. So this will be our first sketch. We'll make a circle of, what was the diameter again? It's 15 millimeter. Okay, 15 millimeter is the diameter. Now let's extrude this one. So in the extrude process, we need to keep in mind a thing about making the material frozen, or else as you can see in the figure, it will be one structure. If it's a single structure, we won't be able to apply two forces, so we need to froze two parts separately. Okay, this is the extrude process. And what was the length? First one is 180 millimeter. 180 millimeter. Okay, so let's generate. As you can see, yes, all right. Now let's make another sketch in this space. Circle. Okay. So what was the dimension again? It's 10 millimeter diameter, of course. It's 10. Okay, now let's extrude this one. So to extrude this one, we need to gain that frozen property to make two different separate things. So I guess it was around 200 millimeter. Yes, that's correct. 100 millimeter at frozen. Now let's generate. Okay, so this is our basic geometry. Yes, it's correct. When in the figure, a little smaller. Yeah, Yes, it's all right. Now let's start modeling. It takes a few seconds to get into the modeling process. Here it is. Here is our model. So this is our model. So first thing we'll do is in this solid we'll apply our material that we have been assigned. That's the Poisson ratio and Poisson ratio and Young's modulus 1. Yes, we assigned it here, and the second part also we'll do the same. So after that we'll mesh it. Mesh is important. We'll try to mesh the whole structure. So generate mesh. Great. So this is our mesh part figure. Now next thing, so this is our mesh part and structure. So next thing, we need to fix the bigger part of the model, this space. Okay. So let's go to static structure, environment. There is fixed the face, this space. Yes, apply. So this space is fixed. That's great. Now let's add force to these two areas in the structure. So again, static structure, force. Here we need to select the face. Okay, so this face will apply, what was the magnitude? It was 5 kilonewton, which will be 5000 Newton. Okay. Apply. So we did apply force. So here, oh, it's in the opposite direction, right? It's being got applied in the opposite direction. You need to change the direction. For that, we'll just add a minus to it. No, it's in the opposite direction. Yes, that's how it's been given in the figure. Yes, the inward direction. Yes, it's correct. Now let's add force again to this face. So what was it? It's 2 kilonewton. Okay, so from learning from our mistake, we'll give the minus symbol first for the direction. Okay. Let's apply. Right. Wait. Okay. So this was it. All the three forces and a fixed structure. So that's what was in the question. So we figure out the question. Now let's get to the solution. We need to determine the nodal displacement at point B and C. Okay. So for that, we need, let's see the total deformation first, and then add directional deformation. So for the directional deformation, I'll specify specify the geometry. Yes, apply. So here the directional deformation results will come in this exact face. Now for this second face, we'll do it again. Let's select the face and apply. For this directional deformation will be applied in this face. Let's also apply this. That will do. Let's solve it. Now let's wait for the solution to be resulted. It's done. So as you can see, this is the total deformation. Let's say 100 and about 10 seconds. We can see the simulation and the force is being applied in these two faces. It compresses. Okay, and when we see the first directional deformation, you can see in this face gets compressed. Yes. And in the second phase, when it's applied here, we can see first phase means this first body gets compressed in this drawing. Okay. Showing only the first part because as we have had frozen to that area, that's why, and in the total information we can see the whole body, how it's get deformed during both in part 1, what was it, in point B and point C. You can see that when the force has been applied in point B and C, it gets totally deformed. And when we take the section of, let's say, in the B part, yes, in the B part, you can see it's getting deformed slowly and slowly. This is the maximum point and this is the minimum. It's how much it can be deformed. And the negative symbol is specifying the direction, nothing more, nothing less. And the C point also, this is getting deformed. So that was what I have been assigned today. Thank you. Hope you enjoyed it. Thank you very much.